The broadcast is now starting.
All right, welcome to the March GoldSim webinar. Today we've got a really nice presentation that will be done by Roald Strand, who is a senior hydrogeochemist at Golder & Associates. And today's topic is simulation of high ionic strength solutions. Like all other webinars, I'll be recording this one and posting the recording in our webinar archive page. And also, we would like to take a moment after the presentation to answer any questions. So if you do have questions, it's fine if you ask them during, but preferred if you ask them at the end, and then we can field those questions at that time. So now I'll turn the time over to Roald Strand.
Thanks a lot, Jason. Hi, everybody. I'll just give a little bit of background on myself. I'm a hydrogeochemist. I worked for Clone, Cripp, and Berger for about 12 years, and I've just recently moved over to Golder. A lot of the work that I'll be presenting today is work that I've done in concert with the staff at KCB or Clone, and recently we rebuilt all of the systems that I'm presenting here today at Golder. It's not something that can't be replicated. But it does take a fair bit of effort to get to a place where you're comfortable with what's being done, I suppose, or what's being calculated. Today I'm going to be walking through a model that I built for my master's work, which is basically a replication of a titration. I performed some titrations at the UQ campus at the landfill laboratory. Basically, the titration was to take some seawater samples or rebuild some seawater, then dose it with sodium hydroxide, and then subsequently run a titration where we would be lowering the pH from a high pH of about 10.3 to 10.9 down to about past 5, or so all the way through the pH range. Now, the process that I'm going to be talking about here is primarily the equilibration systems. And the equilibration systems are basically in this chemistry container. From a conceptual point of view, what the process does, or what the calculations do, is we calculate the free ion content, which is basically in this box. This is just a conceptual model, roughly, where we have a number of different ions in an uncomplexed format, and then we calculate how much, what percentage of those go into a complexed form. And then subsequent to that, we find out how much of those complexes reform into minerals in a couple of different ways. So this is a little bit of a simplification, but basically there's a similar process that goes from free ions to complexes, and then a similar process that goes from complexes to minerals. There's also a secondary process that's basically a direct precipitation process, where if a complex goes beyond the solubility limit, that there's a direct precipitation mechanic as well, which basically just removes mass from solution very rapidly. Basically, there's not really too much else to talk about here. I'm going to dive into this chemistry container, and I'll show you how we have to start off. First of all, there's a number of inputs, as you can imagine. So the inputs that we're currently that I use are temperature, elevation, the area of the surface of the container, which is exposed to atmospheric conditions, the depth of the system. So in this case, it was a really small titration container. It's only 7 centimeters. The dynamic volume, which is basically the volume linked back to this volume here, and the air pressure, which stems from the elevation, and other water quality parameters such as PE. Now, unfortunately, this is one area that I'm trying to improve on. Realistically, it would be fantastic if we were able to do predictions on PE or allow the relative ratio of the ratios of a redox pair to govern the PE, but unfortunately, we can't really do that at this point. Instead, we're actually using PE as a driver, which then, through the Nernst Equation, actually governs the relative ratios of redox pairs, and I'll get into that in a minute. So in this model, we're using a time step of 1 second. A lot of this is sort of adjustable, but it doesn't really matter at this point. It's just what it's built for at this point, because this model is for a very, very small system. In reality, normally we're using these models to simulate processes on a mine site where there's significantly greater volumes, and the change over one time step really should be kind of commensurate with the size of the system. Normally we use 1 day, but in some cases it could even go up to like a week, and it might even go down to as low as an hour, I suppose. Now, one other input is we need to include the charge of each of the different species. So this is actually a good point also to mention what species we're actually going to be simulating. So we've got the majors up front, calcium, magnesium, potassium, etc., through to the inorganic carbonate species, a couple of anions, and then the metals, and then we get down to, at the bottom there's cyanide species, and the nitrogen species. This is that kind of a protracted list because realistically there's a whole lot more complexes that we're going to be looking at as well. And actually maybe I'll just go through that right now. So this is the list of complexes we're simulating. Now this is going to be a little bit more of an extensive list, and I'm sure you won't be able to read all these, but it's just to give you an idea of the number of different interactions we're simulating. So up front we've got the aluminum species. So these are basically sequentially added hydroxide species for aluminum. Then we've got sequentially increasing fluoride species, calcium species, cadmium species, copper, cobalt, iron, a whole whack of iron species. Iron species speciates quite a lot because of its electropositivity. So there's a lot of attraction between negative and positive electrons there, or species. Then we got magnesium species. Anyway, there's a whole whack of them. So we've got over 110 different species there that we're currently calculating, and these are the preliminary species, and then there's actually more tertiary species after that as well, and we'll get into that in a minute. Now, because we're modeling these systems from a thermodynamic standpoint, one of the first things we need to take into account is our ionic strength and activity coefficients. Now, in order to calculate our ionic strength, it's relatively simple. All we're doing here is taking the molar concentration and multiplying it by the charge squared, and an adjustment for the A constant, which is 0.5. This is a bit of a summary there on ionic strength, no problem there. and then we're moving into the activity coefficients. Now, for this model, I've actually implemented 4 different activity models. We've got the Debye-Huckel standard equation, the extended Debye-Huckel, the Davies equation, and the Watek-Debye model. Now, I just want to point out that unfortunately the topic of this presentation is a little bit misleading. So we're not actually doing super high ionic strength modeling in this case. I was planning on getting a specific ion interaction theory model included on this, and this was specifically for my master's work, but I wasn't able to get it done for this presentation, unfortunately. There are some limitations actually in terms of what we can actually do with the specific ion interaction theory, because there's some limitations on what parameterization is applicable, and unfortunately, given the ion set that we're dealing with a large number of divalent species, the specific ion interaction theory is less applicable. So, for example, the sulfate is problematic, as well as the carbonate, and then all of these metals. There's actually very little data for the interaction parameters for the metals. So there's limited applicability for the specific ion interaction theory, unfortunately. We're going to work around that, but there are some serious limitations, and I don't think there's any primary research being done at this point to expand that data set. Now, I just want to start talking about a little bit about how the model and how the actual algorithms work. I think the best place to do that is actually in the water sub. So this is just a water sub model. Now, all we're doing for the water submodel is we're basically calculating a few key parameters. First of all, this is the ion activity product for the water, And this is basically, this is a chemistry water balance rather than a standard water balance where we're looking at hydrology and the movement of water. This is a chemistry water balance where we're actually looking at the ion activity product and whether or not water is actually forming or deforming, like as formation of H2O or a dissociation of H2O, and this occurs under different circumstances. So this isn't really very complex stuff at this point. This is just the ion activity product divided by the kW for water. That doesn't, I think, lead into anything. It's just a separate indicator of what's actually happening. But then in terms of water formation and water dissociation, this is where the kind of key crux and the basic algorithm starts to take place. And this algorithm is actually applied throughout the entire model, and it's really based on Bronsted,'s Johannes Bronsted,'s observation that ions that have different electrical charges interact more significantly than ions that don't have a charge. And so that's really kind of the crux of this whole model is we're basically working with the observation that when there's a positive ion, it will interact with a negative ion, and that's what we're going to see here. Now this is unfortunately a pretty not a very easy way to understand it, but basically all we're doing here is we're taking a very simple relationship where we're multiplying the OH times the H to get the KW, and we know that that's a constant relationship. And so if we add a delta term into that, well, then we would say like OH plus delta OH multiplied by H plus delta OH or delta H. That gives us a capability to look at the differential in terms of an approach to equilibrium, or how much do we need to add or subtract in order to get to equilibrium. And if we do some simplification on the algebra and introduce a solvent formula, which is basically the quadratic equation, then we can solve for the unknown, which is the delta term in every single case. Now I know that may be a simplification of how it's done, but trust me that it works, and actually maybe what I can do, I'll just do a very quick check here. I don't know if you guys can see this screen. I'm just opening up PowerPoint, and I'll just give you a very brief walkthrough of how that algorithm actually pans out, because it's a little bit complicated, but it's worth knowing. All right, so this is basically the ion interaction approach. So really what we're looking at is the positive interacting with the negative. And here's a perfect example. So this is where it all started. It all started with a calcium and sulfate observation that these two parameters weren't going to be directly influenced by pH. And so what we needed to do is, when we first started modeling, we needed to figure out a way to implement an algorithm that would solve for a condition that wasn't directly related to a pH. And this actually started a ball rolling, which has been rolling for about 10 years now. But this is basically how it all works. Okay, so we take our two different ions. So we got a positive ion, we got a negative ion. Then what we do is we add a delta term. So we've got a delta term here of dCA2. We've also got a DSO4 here. Now what happens is when you multiply these together, you have to eventually get to the KSP if you're in oversaturation condition. But if you're in the undersaturation condition and there is gypsum present, then we know that we can add dissolved gypsum to the formula, or we can add dissolved gypsum to the water quality to get up to the point of the solubility limit. Now what this does is it actually calculates how much that is, and this is kind of the overall crux of the entire process. Now fortunately it can be applied to a broad number of cases, including sequential addition, hydroxide on iron, and a number of different other things that we'll get into in a minute. Now basically this is how it looks like once you multiply those together, and then all we're going to do is we're going to just resolve this, setting dCA equal to DSO4 because of stoichiometry. And then basically what falls out is we've got one equation with one unknown. The unknown is DCA2 plus, and we can solve that using the quadratic equation, and that's basically the nuts and bolts of it. Now what we're going to actually do is we're going to apply that same concept to basically almost every single interaction that we possibly can, and we're going to see how that turns out. So we did that for water. Sorry, if I'll just go back here for 1 second, but basically we're applying that same methodology here for water. So we've got the quadratic equation. The quadratic equation in this case, the B term is OH plus H plus. Then we're gonna square that. So it's B squared minus square root of B squared minus 4AC, and this is A in this case is 1, and C in this case is OH times H plus minus the KW. Divided by 2, and that gives us our delta term. Now, if you understand the way that the quadratic equation works is that there's a plus and minus term. Now, if you invert the signs, because we have to solve for the condition of approaching equilibrium from the undersaturated side and approaching equilibrium from the oversaturated side, if you reverse the signs, we just get a slight variation of that same equation, and all we're doing here is we've got the negative H plus OH, and then plus the square root of those same things. And basically that gives us our reverse condition where we're basically approaching equilibrium from the opposite side. All right, so that's how basically that is applied. And now I just want to show where we're doing it in a couple of other ways. So now the alkalinity system is slightly different from the rest of the model because the alkalinity system is actually very dependent on processes regarding surface gas exchange, such as carbon dioxide, and the alkalinity system is actually very important because it's the primary source of protonation. And when we're protonating in solution, what we're doing is we're basically extracting an H plus from the free ion set, and we're adding it to a complex mass of inorganic carbon. And the way that this works is very similar. It's basically just using all the same algorithms as we noticed for the water interactions, and it's basically just the same thing here. All we're doing is we're taking the H plus the CO3, adding the square root of the B squared minus 4AC, and that gives us our approach to equilibrium from that point of view. And then we do the same thing but opposite for the CO3 to HCO3. Now, for the alkalinity system or the inorganic carbon system, there's a number of different interactions taking place. There's a sequential addition of protons to inorganic carbon as CO3. So we go from CO3 to HCO3, then we go from HCO3 to H2CO3. And once we're at H2CO3, then there's a possibility of degassing and contribution of CO2 as a gaseous phase. And what that would do in this case, because I was modeling for a small enclosed system, what that was doing is that was increasing the partial pressure of the CO2 in the headspace of the titration vessel. Now that was this is a little bit more complicated than most systems. In a normal case, what we would do is we would call it an open system, and basically all that would do is it would set a maximum H2CO3 concentration, which we would expect the system to approach in basically every situation. Now, there's a possibility that the pH will affect that, and that is one thing that we're kind of dealing with in some ways. So the one way that we're dealing with that is that there's a possibility of the H2CO3 concentration going up, but then what it'll do is it'll enforce a change on the it'll enforce a CO2 dissolution rate, basically. So it'll always be adhered to, but not always in the same time step. So there's a possibility that there's a brief period or in a few different time steps where the H2CO3 concentration will exceed what is expected. But it'll always get back to it. All right, now I want to get into the more complex part, and sorry, that's a pun, but it is more complex because this is more technically challenging. Now, what we're going to talk about here is the complexation. Now, this is going to get a little bit hairy because it is hairy, but we'll talk about the parameters first. Now, in terms of the parameterization, the way that this model is set up is basically as I mentioned before, we're using the PE as an input for the model. So we're using the Nernst equation to calculate the different quantities of the different valences of each of the different metals shown here. So we've got arsenic, copper, chromium, selenium, iron, and manganese. And it looks like a couple of these aren't actually set up, but that's okay because the actual Nernst equation application is still valid. So the way that the Nernst equation works is we're taking the EH that we're assuming in the solution, that's just calculated off the PE. Then we subtract the E naught value of arsenic, and this is a known standard potential at 25 degrees and standard pressure. And then we just do a quick calculation the arsenic of this is just a conversion to account for the sum of both of the species, both of the valence states to add up to the arsenic concentration. And from there, we can also calculate the alternate valence state. Now, the way that this works is it basically just takes the current concentration and distributes between each of the different valence sets. Now, the reason why this is important is because each of the different valence metals has a different property when it comes to complexation. And we're going to see that in a minute. In terms of the other parameters, we've got a whole range of other parameters here. You can see we've got calcium activity, magnesium activity, chloride activity, et cetera, et cetera. And basically the way that this works is we're just extracting the molecular or the molar concentration and multiplying by the activity subcoefficient. So that was basically coming from the activity coefficient that we've selected. So in this case, the activity model that we've selected is number 4. Number 4 is the Watek-Debye model, I think. Let's just check that. Activity model 4 is Watek-Debye, that's correct. And basically the Watek-Debye activity coefficient is solved in this case for every one of the free ion parameters. Now we're not currently solving the activity coefficients for the complex states. The complex states are assumed at this point to be having an activity coefficient of 1. And I'm doing a little bit of research to find out whether or not that is an appropriate assumption or not. Now, what happens is we take our parameters. These are all of our free ion parameters in their thermodynamically relevant state of activity. And then subsequently, we're going to start our calculations for the complexation. Now, if you were listening before, I mentioned that we're using the quadratic equation. Now, the quadratic equation is basically separated into three different terms. There's an A term, a B term, and a C term. Now, if we recall, I'll say it slowly. The quadratic equation is negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, those are basically these. So we've got negative b plus or minus square root of b squared minus 4ac all over 2a. Now, what we're going to see is how all of those different algorithms fit into those different terms. Now, this is why I'm saying it's a little bit complicated, because it's quite difficult to follow. But basically, every single one of the complexes has, in this case, a value of 1 for A. For B, there's a different term. Now, this is where it starts getting a little bit tricky. But basically, we have to resolve every single one of the complexation equations for each one of the complexes. So in the case of AlOH, for example, this is our first addition of OH to the free ion species of aluminum. So we've got aluminum plus hydroxide and the KEQ for aluminum hydroxide. And then for subsequent reactions for aluminum, we're doing sequential addition, hydroxide addition. So this just basically takes the precursor, which we solved here, and it applies it here. So we've got our complex concentration or complex activity. I've allowed a provision for calculating complexation activity, but we're actually just currently using the concentration. So this is a bit of a misnomer at this point, but it's okay. Now, all we're doing for the sequential addition ones is we're basically just adding one more hydroxide in each subsequent, each of these reactions is basically calculating the precursor for the following one. And that's basically how these work. And this is just remember that this is all we're doing at this point is we're calculating the B term, and we've also got to calculate the C term. Now you'll notice that there's quite a large number of calculations here. So this it's not all that complex, to be honest. It's actually just a matter of following through and getting doing it in a sequential format. And that was actually really a really big it was a really important efficiency standard. So the way that I calculated this, all of these, they're in a matrix format, and the matrix format is really valuable, and that was one of the reasons why GoldSim is such a good program for using this or for doing it this way. And now finally for the C term, it's very similar. This is all we're doing here is we're calculating the C term. And just to keep in mind now, when we're calculating the quadratic equation, we're taking the A term, the B term, and the C term, combining all of these, and this is just the representative. Each one of these is just the representation of the C term. So this is subsequently calculated in the next calculation. Now you can notice that there's a lot of different, there's quite a lot of references to the KEQ. Now I want to point out that the KEQ is actually the inversion of the thermodynamic constant. So we're taking the inverted KEQ value, and the way that we've calculated these is we basically go into a thermodynamic database, extract the relevant equilibrium constant, and stick it into a table. Now this isn't going to be very intuitive, but basically what we've got is we've got the same number of KEQs as we have complexes, and these are the KEQs, the inverted KEQs for each one of the constants at a different temperature range. So what we've got is we've got the temperature in Kelvin here, and we're basically calculating the equilibrium constant over a temperature range of 100 degrees Celsius. Sorry to the Americans, but this allows us to calculate the thermodynamic constraints and complexation over a broader range of temperature than what we would normally assume based on just the standard climate. So the standard climate might be anywhere between, I don't know, 0 degrees and 25 or something like that. But this would allow us to calculate the speciation over a range up to 100 degrees Celsius. Now, I just want to point out that this is basically the quadratic equation again. So we've got negative b, where we've got b squared minus, or sorry, we've got b minus square root of b squared minus 4ac all over 2a. And that's basically the application of the quadratic equation again. And all we're doing again is we're looking at the interaction between a positive ion and a negative ion from the perspective that even after you add, for example, a hydroxide species to aluminum, you're adding 3 plus minus 1. So that's going to give you a valence, your complex valence of +2. So that +2 can still interact with another negative ion. So it's going to keep adding another hydroxide onto that or whatever. Now, one thing that we haven't done at this point is we haven't looked at mixes. So if for example, there are some cases where, like iron, for example, will complex with chloride and hydroxide, and I have yet to address that in these models. But from what I understand, it's a relatively low percentage of basically the free ion would be relatively less distributed towards those mixed species. So I don't think we're losing a lot of accuracy at this point. Now, the way that this complex system works is basically we're solving this quadratic equation for each one of those species, as we talked about before, and those form a complex. Now, the complex basically is just a new vector, and we've distributed the mass from free ions into a complex form. And that's basically what I'm showing here. So for example, in the free ions, we might have copper, hydroxide, and sulfate, for example. And then once those complex, we're going to form these new species. Now, some of these species will actually be neutral, and this is where where Sechenot's equations start to apply. And basically, for Sechenot, that is basically the assumption that we get a one activity because there's limited ionic interactions, and basically that just means that the thermodynamic constraints that might otherwise be applicable based on Coulomb's law are no longer applicable, and we can just assume an activity of 1. Now, we're assuming an activity of 1 for even the negative species, and so that is one of the drawbacks that the model is currently facing, and that is something that we may be improving in the future. Now, once we've got a set of complexes, so I want to just point out here that that some of these minerals are a little bit more difficult to solve. These have some pretty complex stoichiometry. So, for example, this is malachite and this is jarosite, and I want to point out that jarosite has a total stoichiometry of 1, 2, 3, 4, 5, 6, 12. So there's 12 different species. Now, previously in previous iterations of the models that we built, this type of equation would be very, very difficult to solve. It would require a polynomial of order 12, which is, I'm just going to say that it's impossible to solve. There is actually no way to solve that. But if we break this down into a series of smaller parts that can be individually calculated, there's a possibility that we can actually solve this in a much more robust way. Now, what I want to point out is FeOH3 here is one of the precursors for jarosite, and if we take out 2 of these guys, then that actually knocks out a really big number of these, and then what we're actually left with is FeSO4 and NaSO4, and you'll notice if we go back into our complexation parameter list, we actually have both of those, and this was actually a little bit of an exciting moment for me when we were trying to simulate jarosite, because it was an element, or it was a mineral that was that has been extremely difficult to accurately look at in the past. Now, I just want to point out here that we've got this Fe3SO4. This just basically means Fe3 plus, so the valence state, and then the SO4 on the end of it. So we've got iron sulfate, and the other one we were looking for is sodium sulfate, and we've actually got that one as well. We just got to find it here. There it is, right there. So sodium sulfate. Now this is a charged species. This is a -1 charged species, and the Fe3SO4 is a +1 charged species. So what we actually can figure out here is that if we have goethite present as FeOH3 or ferrohydrite present as FeOH3, if we can also calculate the concentrations of FeSO4 and NaSO4, we've got all the precursors for jarosite. And it actually falls out very nicely in terms of algorithms, because as long as the FeOH3 is present, this is present as a solid form, then the rest of it just basically falls out using the same equation that we've talked about previously. Very similarly for this malachite equation, basically all we're doing is we're taking two different species. We're taking Cu3 and CuOH2, and we're combining them, and we're basically getting a malachite formation there. Now, I just want to point out that all of those elements that we've just talked about, or all of those minerals that we've just talked about, follow a similar process of using the same algorithm that we did before to create a formation constant, or to be calculated with a formation constant. But there's also a different possibility. The different possibility is when there's a direct precipitation, when a complex concentration exceeds the solubility limit. And I'm going to just talk about that briefly. So what happens with that is we've got a direct flux mineral K. So what we've calculated is the K for a specific species. Now this is actually otherwise termed a solubility constant. And basically all that happens there is as I mentioned before, is when the concentration exceeds the solubility limit, it's just multiplied by the reaction rate, and the model will actually extract from solution the amount that is in exceedance of the solubility limit. And then if the solubility limit if the concentration in the complex form ever goes below the solubility limit, then we have a direct dissolution of the mineral form back into the complex form. So it would be just a conversion of say, for example, CaSO4 solid with a subscript S to CaSO4 subscript aqueous. And that's basically just that how the terminology works. Okay, now I just want to talk a little bit about how the logistics works, because the logistics is actually quite a complicated maneuvering as well. Basically, what we're doing for the logistics, because what we're doing is we're actually moving mass from a free ion state into a complex state and then subsequently into a mineral state is we need to keep track of our mass. And the mass is actually, it's really, really important to keep track of the mass, because otherwise we end up in a solution, or end up in a difficult situation where there's where we have we don't have conservation of mass. And if we don't have conservation of mass, basically the entire model is shot. So what we need to do is we need to move mass and track it appropriately, so that we're not double accounting anywhere, and we're not losing mass. Now, the way that this works is a little bit tricky. Now, the first thing that happens is that we have solid, and this is actually in the free phase. This is free ion phase. And I want to point out that when new mass is being added to the solid container, so for example, if you were modeling a mine site and there is sulfide oxidation occurring, or there is dissolved flow moving into a pond or whatever that you wanted to simulate, then that would capture this bucket here, this element here would capture all of that movement of mass. And what we're going to do is that we're then going to distribute it. So what we've calculated here is the free ion concentration. Now, this concentration is actually not actually at equilibrium. This is kind of like in every single time step, it's going to change. And I've made some allowances for that in this model, and now I'm going to show you some results in a minute. But basically, this free ion concentration is never going to be at equilibrium. It's always going to be sort of slightly off equilibrium. Now, in a mine site where you're dealing with a fairly large pond, for example, that's not going to be very significantly out of balance. So it might be like 1% or 2% out of balance. But realistically, that's a completely reasonable error range to be operating in. But what we're going to do is we're going to now distribute that according to this process. Now, the way that works is basically we're going to take all of our different, so for the inorganic carbon and the hydroxide species, I use this array here. Now, the reason why is because all of these elements are actually explicitly modeled. And the reason why I use a different array for explicitly modeled, species is because, well, actually, I don't really have a good reason for it. But I think that it works better because when you don't use it that way, this one get mixed. This one actually has to be utilized. The complex flux is utilized in a couple of different areas. But basically, what I want to do is this keeps the calculations straight. So all of the loss array and the gain array are only for elements that are explicitly modeled, and for the complexation, these are actually all for direct flux between the different species states in terms of complexes and minerals. Now, I know that that's going to be a little bit hard to follow, but I think that it's important just to understand that these are just for the explicitly modeled species, and these ones and the subsequent gain and loss arrays are going to be for distribution of mass between the minerals in the complex form. Now, the way that this works for the complex forms is different. These what we're going to do is we have to use a conversion table, and the conversion table basically sums all of the stoichiometry for each different complex and then attributes it to all of the different species. So, for example, if we just want to have a look here, let's look at cobalt chloride. Now, for cobalt chloride, we're going to expect that there's one cobalt and one chloride. So there's a 1 there, and that's for chloride. And we look further along the table, and there's a 1 for cobalt. So the point of this is basically to attribute all the different complex stoichiometry in terms of molecular mass to each of the different E vector elements. And if you kind of understand why I'm doing that, then it's to account for the stoichiometric mass of conversion of an ionic species into a complex species. And the way that this works is basically all I'm going to be doing is multiplying, or I'm taking the sum column for the complex E conversion multiplied by the form, which is the formation constant, which is what we calculated up here. I know that I talked about this being complicated, and I'm very, very sorry. It's just there's probably a lot to cover, and I'm going through this at a pretty rapid pace. And I apologize, it's just there's a lot to cover. But basically all we're talking about here is the formation and the deformation, and we're accounting for the mass flux or the mass change through a conversion table. Okay, and now this applies to the solute container. Okay, now what we're doing here is that once we've extracted that mass from the free ion concentration, we're putting it into a complex bucket. And then once we're in the complex bucket, we can then go back and say, well, what are we going to be putting into our mineral bucket? So this is our mineral bucket. We've got a complex bucket here, and then we've got the solute as free species or free ions. And in terms of the mineral loss, that comes from the mineral loss array and the mineral complex gain array, and those are just right here. And we're just basically informing these arrays from the mineral formation rates. And the way that looks is relatively straightforward. But basically, if we've got a mineral formation, for example, if we've got a mineral formation of gibbsite, which is AlOH3, then the formation rate of gibbsite is going to directly subtract from the AlOH species, AlOH3 complex, sorry. Similarly, if we've got like allanite forming, for example, so when we've got allanite forming, allanite is actually a much more complicated species than AlSO4. So what we're going to be doing is we're going to be extracting 1 mole of AlSO4, and we're also going to be extracting AlOH3 should actually be attributing to the allanite as well. So this should actually be up there as well. So that's an error that I've got to fix. But I just want to point out that we've got a number of other species here. So we've got gypsum. So we've got gypsum formation, and we're extracting it from the CaSO4. Let's just have a color. Let's just look at jarosite, for example. So for jarosite, if we have the formation of jarosite, we're going to be extracting from NaSO4 as one of the precursors, as well as FeSO4 as one of the other precursors. Where is FeSO4? Looks like this is an incomplete model. I'm very, very sorry. That's my fault. I'm presenting a model with errors in it. That's not very good. But you can see that it's you can see that I've accounted for it down here. So what there should actually be is there should actually be a mineral formation for stoichiometrically relevant extraction from each one of these. So this one should have jarosite on it, and this one should have allanite on it. It looks like this is an older model. I did actually correct that in a subsequent one, but I apologize. So anyway, that's basically how this process works, and there's a lot of calculations involved in each one of these chemistry containers, but realistically, they do work pretty well. I just want to point out that this one, for example, has actually, I'm just going to sort of show some of what this sort of looks like. So as I mentioned before, this one is a titration. So what is actually happening here is there's a change in the pH to a higher concentration, or sorry, a more. Let me just see if I have pH somewhere in here. It doesn't really matter, but there's one up here. Okay, so this is basically what I was talking about. So the model, basically what it's doing here is it's going from an initial state of pH 3, where we're going to add some OH to the system. We get up to around up here, and then what we're going to be doing is titrating down. So the red line is the recorded pH in the titration, and the green line is the predicted pH. Now you'll notice that this is offset, and there's still a little bit of error. Now that's obviously quite a large amount of error, but I want to point out that this is one of the most extreme situations that I've ever had to model, and we've actually been very successful where what we're modeling is a much bigger system. The reason why this is there's a lot of error here is because or one of the reasons why there's a fair bit of error here that's actually observable is because in the titration there was an unrecorded interaction with carbonate or inorganic carbonate in the in the titration vessel and as I was preparing the solutions. And so what there is there's error being incorporated into the actual titration that I was not able to capture in the modeling. Now I have tried to capture it in the modeling, but I haven't been able to do so adequately at this point. But we can still talk about this because this is the best model that I've currently got, and we can also talk about the complexation. So I want to show how the complexes look. So here's how the complexes look once we are undergoing at the titration. Now there's a lot of different lines on here, and I apologize for this, and I'll go into some little bit more detail that's a little bit easier to see in a second. But basically what we can see here is that there's a substantial change in some species while there's less substantial change in others. Now, this is really interesting. Okay, so this line here, this pink line here is actually HSO4. And what happens is every time the titration progresses, so the auto titrator is actually adding a very small aliquot of quite concentrated HCl to the solution. And every time that aliquot is entering the solution, there's a very rapid change in the concentration of H+. Now, what actually happens is that the model is capturing that quite adequately. So what's actually happening is that the pH is actually jumping around. And I just want to point this out again, back in this situation here. So if we actually look at the predicted pH, what's actually happening is that exact thing is happening. Every time an aliquot of concentrated HCl hits the solution, there's a very rapid change in pH, and then there's an immediate recovery phase. Now, I just want to point out that this is actually the model recovering. So here's what happens: is that you start at a basic concentration, you add concentrated HCl to the solution, and then the model is going through a recovery phase. And this is actually very similar to what's actually happening in solution. There's actually a chemical change occurring in solution where the H+ is dissociating from the chloride molecule or the chloride ion, and all of those H+ are actually being recaptured by hydroxide. And there's a very subtle shift in the hydroxide concentration because you're starting with a very concentrated form. And basically what's happening is that all of your H+ are being consumed and your pH recovers to around the same level. Now, what I want to point out on this is that I'm not trying to calibrate to this individual shift. I'm actually trying to calibrate to this down here. And what we were able to get to, this isn't, I think, one of the best models that I've got, but it's pretty good. What we're trying to get to is down here, and we are within, so our recorded pH is 3.897, and we were able to get to 3.841. So we're pretty close in terms of the overall calibration, but I do note that there are some gaps while the model is when there's an offset in the update, and also there is some gaps, and this is primarily due to an unaccounted for quantity of inorganic carbon in the actual titration vessel that I was not able to adequately quantify. Now, in terms of the complexation, this is a really important part, but basically I'm just going to show you some of the interesting sort of outcomes that we can figure out from this type of modeling. Now, this is actually the complex alkalinity. So these are species that include hydroxide. So for example, we've got free hydroxide up top, we've got magnesium hydroxide, sodium hydroxide, calcium hydroxide, and potassium hydroxide. Now, what I want to show here is pretty interesting. So each time an aliquot of HCl goes into solution, we get this, we get a little dip here. But what I want to point out is that as the titration progresses, we start to see a energetic prevalence of a dissociation between the ionic form or the complex form and the hydroxide, because what's actually happening is that as the pH is changing in the solution, or as more hydrochloric acid is being added to solution, what's actually happening is that it's becoming more energetically favorable for there to be a dissociation between the hydroxide form and the positive cation. And then once we hit around the midpoint in the titration, we're actually getting a very rapid decrease in the prevalence of these hydroxide containing species. So what we actually get is that around the midpoint might be right around here, for example, the there's a rapid shift and a complete dissociation, or not a complete dissociation. You can see that there's still some of these forms still present, even once we've gone down to a pH of around 4 or 5 or whatever. And this is actually to be expected. So it's very unfavorable for there to be sodium hydroxide as a strong base in a solution that has a pH of around 4. But this is not uncommon. It's just energetically unfavorable, but it's not energetically implausible. And so what we see is that we are moving from a state of energetic favorability to a state of energetic unfavorability. And that's the beauty of thermodynamics, is that you're really accounting for the statistical distribution of species within a solution. Now, this was the complex alkalinity, but I also want to show what some other complex species we can look at, and this one's pretty interesting as well. So this one we can see that the top likely the most energetically favorable species is sodium chloride. Now, we all think about sodium chloride as being a strong a salt composed of a strong acid and strong base, and that's fair. There's a very strong tendency for sodium chloride to dissolve in solution. But realistically, what we don't normally think about is sodium chloride being a complex form, which is actually in an aqueous form. So this is sodium chloride as an aqueous form. So this would be, if you were looking at this as a chemical, it would be NaCl subscript aqueous. And that's going to be the same for all of these here. So we've got magnesium chloride. Now that's a charged species as a -1 or a +1 charged species. Here's magnesium sulfate. You can see magnesium sulfate is quite prevalent, and that's quite interesting. And then we've also got calcium chloride, as well as magnesium hydroxide. And so you can see these ones here, we captured them before as the aqueous species, but these are I just want to show how the difference here between the hydroxide containing species varies from the non-hydroxide or the non-H plus containing species, which are basically very steady as the titration progresses. Now, the reason why some of these are changing ever so slightly, so you'll notice that there's a slight little drop there in the sodium chloride. Now, the reason why that these are actually changing in concentration is because what we're actually adding to the titration vessel is concentrated sodium chloride, or sorry, concentrated hydrochloric acid. And when we're adding that, we're actually diluting other species. So we're actually diluting the sodium concentration, and we're actually diluting the magnesium concentration. We're actually diluting like all of these concentrations. The only one that we're actually not diluting is chloride. And what we can see here is we can just see that there's an ever so subtle shift in the non-pH dependent species, and in the pH dependent species there's a very, very substantial shift. Of course, this is where the pH is around 8 to 10 up here, so this is around 8 to 10 pH. We go through a shift where we go through the midpoint of the titration, and unfortunately the titration data recovery, the way that the machine, the auto titrator, and the data recovery was set up in the laboratory was not quite as a high resolution as I would have liked. So unfortunately, there's a little bit of unsurety as to how much how much of the actual titration, or how much it had progressed, and especially right around the midpoint, unfortunately, because it would have been really nice to get a little bit more resolution right around the midpoint. But that's just what I'm working with at this point, and that's okay. I am thinking about redoing the titrations in the lab, but that is quite a lot of work that I would have to do to get that organized. So that's currently not on the table. Okay, so basically we've talked a little bit about how this sort of performs, how these complexes look. We can talk a little bit about, for example, what the concentrations look like, but it's not very interesting. I do want to point out that so the model in terms of the initial sort of like quantification of the complexes and whatnot, it forms very rapidly. So we're starting with an initial condition here of, well, in this case, this is chloride at like 20,000 milligrams per liter. So this is the most, this was the most concentrated solution that I prepared, and it's representative of seawater at around 0.7 ionic strength. So this has about 20,000 milligrams per liter chloride, 10,000 milligrams per liter sodium, and then the rest of the species are distributed around 2 to 3,000 or lower. And this is representative of seawater. And now the interesting thing about seawater is that it is quite high ionic strength, so we're going to have quite a lot of distribution between the species that we were talking about before, but the aqueous species. But in terms of sulfide oxidation and applying this to a mine site, for example, where there's sulfide oxidation occurring, there's equally good representation of the metal sulfate complexes. However, I will mention that I have seen some solutions recently from a mine in Indonesia that has some ionic strengths of around 1.4, and that's some very, very concentrated stuff. And I'm not sure if my model will be able to manage that appropriately at this point, but I'm going to be trying to investigate that in the near future. So I just want to point out here that this, again, as I was saying, this is the initial calibration period, and within about four steps, in 4 time steps, we're able to adequately equilibrate, which is quite nice. So in 4 seconds time, this is equilibrated. Now, of course, this is for a very, very small vessel, but because of the way that the system is built with the what I should talk about is what the reaction rate is. Now, the way that the reaction rate is what the reaction rate is actually calculated as a volume per time. And the reason why this is calculated as a volume per time is it allows us to directly apply the reaction rate to the change in concentration of any individual species in order to create an outcome in moles per time. And of course, when you have moles per time, it becomes a rate that can be applied directly to the solid container, because that is the requirement of this type of container. Now, this one is actually in milligrams, but I want to point out that you can rapidly convert weight to molar weight by multiplying by the atomic weights, for example, or dividing by the atomic weights. And so we can convert very readily from a rate in either moles per time or weight per time and apply it directly to the solid container. Now, what I will actually point out here is that this does result in some error. As I mentioned before, you get, depending on the size of the system that you're modeling, excuse me, you can end up with a little bit of error, and the error is generally okay. However, we can with the system as it's currently set up, we've got an iterative system, and that's fine too. Now, the difference between the iterative system, maybe this is important to say, the reason why I'm using an iterative system here is because of the size of the system and the stress that I'm inducing on it. Now, I just want to point out that the stress that we're inducing is actually very, very significant. So I'm just going to create a quick figure here to look at the H plus, and what we're going to see here is if I put this in a logarithmic basis or a logarithmic chart, what we're actually going to see is just how severe the stress is on the system. So in every single one of these titration additions, we're actually inducing a 7-order magnitude stress. Now, like that is a bloody lot of, that is a huge amount of stress on the system, like 7 orders of magnitude stress. So if you can see, this is the actual equilibrated state right down here. So the equilibrated state is at like 1.5 e to the negative 8 milligrams per liter. But under the stress of the titrant addition, we're actually forcing a change of 7 orders of magnitude in a single time step. So that is a very, very significant shift, and we have to be cognizant of what the stresses on a system will be when we're trying to model something in situ. And in my experience, that the stresses may be moderate at around, say, 1 to 5%, and the model will adequately simulate the change back to equilibrium, and realistically, like a 1 to 5% error rate on that is going to be probably the least the least significant error source. There's so many much more substantial error sources when you're modeling like, for example, a mine site or sulfide oxidation in situ, because there's just so many parameters to take into account, and the error between you know, the waste rock and how much water there is and stuff like that. So realistically, like once you've got a chemistry system that's actually working fairly well, as this one is, this is going to be one of the least likely sources of error, which is pretty nice. So you can basically just kind of you know, implement one of these modules, and then basically you've got an equilibration system that's already pre-built into a model, and there's no fuss between using a dynamic link library or trying to communicate with an external system, and it works very nicely just in terms of reliability and also replicability. So as soon as you've got a model set up, or as soon as you've got a module set up, it can basically be replicated across a whole variety of systems without really a lot of fuss. And I think that's been basically an hour of me talking about as fast as I can go, and my voice is starting to get a little bit fuzzy. So I think we're going to cut it off there. But I've basically talked about the concept, how it's applied, what the process of calculation is, how to move from a state of free ions through complexes and through minerals through a gradually more complicated calculation set, and how to distribute mass accordingly so you don't lose mass. Oh, and I just want to point out that if you actually just to point out that we can actually look at the mass. So I just want to show here that in this case I just want to show two things. I'm going to show chloride because we're adding chloride to the solution, and we're also going to look at sodium. Okay, so what we should see here is that they should be relatively steady. Now, as I said before, chloride is actually being reduced in concentration. So this is over the course of the titration. We're adding concentrated HCl, but it's still actually going down in concentration. And again, for sodium, we would expect that to be even less, or see even bigger decrease. And what that looks like in terms of the volume, it's not a very significant change in volume, but there's a small step change. This is a little bit misleading because it's not zeroed. But if we look at it from a zero perspective, we can see that there's a small change in the size of the volume that's actually being modeled here. So we've gone from what is that, 48.2 up to 49, and that was just the water, the saline water in the titration vessel. And I think that's it for today. Now I'm happy to answer any questions. Jason, you're on mute. Do you want to chime in here?
Yeah, thank you very much for the presentation. I was going to ask if you ran this model for one-day time steps. Do you have to change a lot of the model in order for it to do that?
Look, this model has been specifically set up for a very small container with an extraordinarily high amount of stress. So this model uses an iterative time step approach. Now, I will just point out that this is the only model that I've ever built that uses an iterative time step approach. Every other model that I've ever built uses a non-iterative approach, and the non-iterative approach is basically just I use a tolerance system in this one, which it doesn't really matter too much, but because it's kind of outside the scope of this presentation. But basically the way that it works is in every time step, the stress that's induced on the system will be handled by the algorithm to return the system to equilibrium. Now the difference is that in every single time step, you're both adding mass and subtracting mass, and what you end up with is a very fine variance between the actual equilibrium and the stress of the stress on the system in every single time step. So if your system, for example, is continuously loading mass, or it's continuously loading water, there's always going to be this dynamic effect going on. And the chemistry system can only update it for the previous time step. Now that is one of the limitations, and that's why I said that you're always going to have about a 1 to 5% error, and that's real, and we're not ever going to be able to get rid of that. However, I just want to point out that, you know, when you're dealing with you know, like with a very substantial error set, you know, like on the range of kind of like 20 to 50% in terms of like the grain size distribution or whatever else, or how much sulfide is actually present and how much is reacting. Like there's just so many unknowns that realistically, like you know, the 1 to 5% error that you're actually dealing with here is very, very small from a predictive standpoint.
Okay. Yeah.
Now, just in terms of upscaling it to a 1-day time step, it's not that difficult. I couldn't change this to a 1-day time step because the model won't work with the titration system and the way that it works currently. Scaling it up to a 1-day time step is relatively simple. All you need to do is change this time step and then it'll update. But I do highly recommend that you know, like you have to think about the context in which you're modeling and what you're actually modeling for, because there are a pretty broad number of inputs, as you can imagine. I mean, realistically, when you're thinking about the geochemical process and you're thinking about the thermodynamic processes, there's several pretty key elements that go into you know, like an adequate representation. Those ones we've covered a few of them here, but of course there's a few other ones with the alkalinity, you know, the gas exchange as well. And I just want to point out that I'm only looking at carbon dioxide exchange here, but in other models that I've built, we were actually also looking at oxygen exchange and you know, the partial pressure change in carbon dioxide and oxygen as sulfide oxidation occurs, because basically what's happening there is you're basically consuming your oxygen, and your oxygen is actually is converted into carbon dioxide through the degassing process. So I mean, there's always a number. There's like realistically, it's not just something that you can just pick up and do. There is a lot of consideration involved, and I want to point out that you know, my colleagues back at KCB have been incredibly supportive in the production of these models that we've been doing for a number of years, and realistically now, me being at Golder's also been very supportive as well as like my supervisor at UQ in that. So there's been a lot of people who have, you know, been contributing to this type of modeling, and it's certainly not something that you can just simply pick up and just say, today we're building a thermodynamic model. This is realistically what you're looking at here. Is you're looking at 12 years in development. This has been a long time coming, and it's not an easy road. There's an incredible amount of failure and very, very significant obstacles to overcome. And I've dealt with. Yes.
Sorry to interrupt. I have somebody that's getting ready to go that needs to leave, and they had some questions that I wanted to relay to you.
Sure. Let's bash them out.
But I do definitely appreciate.
Please go ahead.
Yeah. So the question is, what thermodynamic tables are you using?
Good. Oh, that's a very good question. So, one of my colleagues, his name is Yuan Tian, and he's a doctor of geochemistry, and he's a fantastic gentleman that I work with here at Golder. I used to work with him back at KCB, as it turns out, as well. He's responsible for doing external calculations for the KEQ database or the thermodynamic database. And basically what he does is he extracts the data from the thermo.dat database that is also used in the GWB program. GWB is the Geochemist Workbench program. So basically this is a well-populated database that is utilized kind of worldwide, and it's been contributed to by many different scientists. But as far as I know, it's the most robust data set for what we actually need. Now, the way that works is that he will go and investigate the database for the appropriate thermodynamic constraints based on the based on the complex that we're looking at. So for example, you'll it's a little bit vague here because these are just a whole bunch of numbers, and you can't actually see what they represent. But every single one of these represents the KEQ or it represents the element that we're trying to form in the complex set. So for example, for ALOH, which is the first one, this is the KEQ this is the temperature dependent inverted KEQ for aluminum hydroxide. And it's not that complicated, but my colleague is extremely quick at putting these together. So he's done the vast majority of these. And this is a calculation that he does, and we've had that checked a number of times or whatever, and it's fine. But realistically, I have to give him credit for putting these together, because this was an easier way. It simplified the calculation. So the alternate way of doing it is not to do the inverted calculation, is just to extract the KEQ directly. But the problem with extracting the KEQ directly is that it results in a more complex C form and B form. So when we do the inverted form, it just makes this calculation a little bit easier. Instead of applying the KEQ directly to a whole number of different terms, we can do it a little bit more easily by doing the inversion. But yeah, the tables are from the thermo.dat database. But realistically, you can use a number of different tables. And I will actually also point out that you don't actually have to calculate all of these complexes. You can actually form minerals directly from the free ions, but it is it's a much simpler calculation, and you can use the exact same algorithms that I was talking about before. We just use this so for example, for calcium sulfate, for example, you can form a mineral directly using the algorithms that I pointed out before to form the mineral. But we're now doing it for complexes because there's some value in understanding how those complexes change as a result of environmental influences.
Okay.
Are there any other questions?
I think that's about it. So yeah, thanks a lot. I didn't see any others from anyone else. So thank you very much for presenting that role. That was interesting. And also, yeah, I can tell that there's been a lot of work and thought put into this. Do you foresee, I guess I should ask just one more question. Where do you foresee this model being applied going forward?
Oh, that's a really good question. My particular interests currently are in in ocean acidification. So I'm really interested in applying these models to carbon dioxide dissolution and trying to make predictions on almost exactly what this model is built for, which is basically looking at high sodium, high chloride solutions, which is saline water, and then the interaction of carbon dioxide. Now that's my personal interest, but realistically, we've had a lot of success in the past applying these models to mine sites. So I don't know if I have. I probably can't talk about specific mine sites that we've been able to do it for because of confidentiality issues. But I will say that that in the past we have been able. Now I just want to point out that this model is quite significantly more advanced than some of the previous ones that we were working with, and as I mentioned before, like this is quite a long process of getting this model up, getting all the research organized and basically putting all the algorithms together and understanding how to actually build it. And realistically, the work that that I did with Brent Usher at KCB was very remarkable. Even in its early days, it was an application that nobody else was doing, and we were able to apply it to, I don't know, maybe like probably 5 or 6 mine sites in Australia, a couple in the Pacific, a few in Asia Pacific, and then a few more in South America, and it's been very successful. Overall it's been very highly highly regarded by the clients that we were working for. Generally speaking, the work was never perfect, but it was always in a kind of a continual state of improvement. However, all of the clients that we did build it for were they were receptive to the fact that it was a relatively new technology, and that was and there were going to be some drawbacks and some downfalls, and so they were largely sensitive to that, and we were able to secure quite a lot of year-on-year funding to continue with the work and to keep the research going. I would say that most of the clients that we built models for originally, which may have been in the last I don't know, like sort of 5-6 years or even 8 years or whatever, are still actually using the models that we built because there's actually such high utility with them.
That's great for using models that were built that long ago.
It
You
is.
don't see that very
It
often,
is.
so that's great.
It's actually. It's actually. I know. I actually sometimes marvel out of myself, and I'm not trying to just toot my own horn here, but I know that when a water balance is built, many times that it's only applicable for a very brief period of time, and then it has to be significantly updated. But we've had some clients come back year on year that the request like minor updates or whatever, but realistically the bulk of the model is and the core kind of components of it that are providing the real value are actually the water quality related aspects of it, and they've been very supportive. So it's been a long journey, but it's also had a lot of successes.
Great. All right, good to hear. Well, thank you very much, Roald, for your great presentation. And if anyone else out there has follow-up questions, feel free to email us um, and at software@goldsim.com, or send us a support request, and we can help you with any follow-up questions that you might have. And I'll obviously just forward these over to Roald, and he can answer them. Um, but Roald, I don't know if maybe you could. I don't know if you want to give your email address out to those on the call.
Sure.
Yeah.
Sure. Yeah. You could. I suppose you could put it on the
Yeah.
on the link on the website if you like. But
Yes.
for anybody listening and they'd like to get in touch, my email is rstrand. That's rstrand at golder.com.au.
Okay, and I'll also send this to everybody in the little chat box so you can get that there. All right. Well, if that's it, then I'll go ahead and close this up, and we'll see you guys for the presentation next month. Thanks a lot, Roald.
Thank you so much, Jason.
All right.
And
Bye.
good. Bye bye, everybody.